Modern autonomous agents make a powerful promise: the ability to search the live web and retrieve real-time data to solve complex tasks. But the immediate reality for developers is often a series of confident fabrications. An agent claims to have searched the web, yet the information it provides is entirely made up. It generates non-existent product links, makes up numbers, and cites dead URLs with certainty. In this terminal simulation, a user requests a product, the agent provides a URL, and hits a 404 error because the product never existed. This failure rate is staggering. Roughly 60% of citations from standard LLM search tools are broken or entirely fabricated. Building reliable applications is impossible when an agent actively lies instead of admitting it cannot complete a task. This unreliability in native web search tools is the single biggest bottleneck preventing true agentic autonomy in production. Developers typically misdiagnose these hallucinations, blaming poor prompting, small context windows, or weak reasoning in the model. That assumption is wrong. Look at this network layer flowchart. The real culprit is an invisible failure occurring long before the model begins to reason. Out-of-the-box tools lack error handling for web blocks. The network failure happens silently, returning a blank context to the model without warning. The agent receives a capture challenge or an empty page, but the system fails to trigger an error state back to the user. This raises a critical question. If the agent receives no data, why does it fabricate specific lies instead of admitting it was blocked? To fix agent hallucinations, developers have to stop adjusting prompts and start engineering network layer retrieval solutions. The modern web is an adversarial environment that actively fights automated agents. The scale of this resistance is massive. Infrastructure providers like Cloudflare block AI crawling on roughly 20% of the web by default. Simple native fetch requests are fundamentally unequipped to bypass these enterprise-grade anti-bot systems. We are now seeing the evolution of anti-bot warfare, the AI labyrinth. Instead of blocking a detected bot, an AI labyrinth traps it in a continuous loop of fabricated and misleading data. Real-world travel sites do this today, serving one price to a bot, while a human user on a mobile device sees the actual rates. This creates a severe compounding danger for AI developers. Your agent ingests and acts upon poisoned data. Relying on standard web access guarantees that your system will be either completely blind or actively misled by modern content delivery networks. Consider the moment an agent hits an anti-bot wall, receives an empty page, and fails to register an error. This triggers a behavior ingrained by reinforcement learning from human feedback, the model's need to please the user. This decision tree shows the mechanical conflict. Penalized for refusing a task, the model attempts to fulfill the prompt even when the context is empty. It pivots to static pre-training weights, pulling from an old, dusty archive to provide an answer. This causes a temporal mismatch, where a model uses training data from 2024 to describe the live state of a website in 2026. This mechanical combination, invisible network blocking and the alignment to please, is the root cause of fabricated URLs and citations. Developers would prefer an agent that simply admits it cannot access a page, but standard models are literally programmed against doing so. Hallucinations are the direct result of alignment features attempting to compensate for severe network retrieval deficits. The architectural solution is to decouple the LLM's inference engine from the web retrieval mechanism entirely. Using the Model Context Protocol, or MCP, we can route agent requests through specialized, dedicated scraping infrastructure. To test this, we prompted a vanilla LLM and an MCP-backed agent with identical tasks targeting 5 sites with heavy anti-bot defenses. The test targets were Rightmove, LinkedIn, the Instagram platform, Amazon, and finally TikTok. The results for the vanilla LLM were a total failure. It was blocked by every single target. Now, consider the MCP-backed agent running those exact same prompts. The MCP agent successfully extracted data across the targets, achieving a near-total success rate. Raw LLM intelligence is useless without a specialized retrieval layer capable of surviving the modern web. The MCP infrastructure succeeds because it uses remote scraping browsers rather than simple fetch requests. These browsers use unique fingerprinting so that each parallel session appears as a distinct, legitimate user. The system injects advanced human mimicking telemetry into the session, including chaotic, unpredictable mouse movements and entirely natural typing cadences. This behavior satisfies anti-bot algorithms, preventing CAPTCHA challenges or AI labyrinths from triggering in the first place. Successful AI web extraction requires engineering the agent to look as chaotic and human as possible at the network layer. Beyond retrieval, we have to solve the challenge of token cost and context window bloat. Many developers drop raw HTML directly into the context window, instantly overloading the model's capacity. HTML junk consumes 99% of the model's memory, leaving almost no room for actual reasoning. The MCP solution is to use a tool that returns purely formatted Markdown, automatically stripping away all HTML tags. For large-scale data, an even more efficient strategy is to avoid using the LLM for parsing entirely. Instead, prompt the LLM to write a custom, localized parser script in Python for the specific target website. The agent executes the script externally, outside its context window, and only ingests the final clean dataset. Delegating parsing to external scripts saves roughly 99% of token costs, making large-scale operations highly scalable. We must clarify a strict compliance constraint. This infrastructure is designed for publicly available data. Deploying agents to scrape data behind logins violates terms and conditions and creates severe legal risk. Agents must only operate on data that is accessible in an unauthenticated incognito window. The "I searched the web" claim is often a fiction born from standard AI infrastructure's inability to survive the adversarial internet. To build production-ready autonomous agents, engineers must stop relying on native LLM search and build decoupled, human-mimicking retrieval architectures via MCP.